Okay, so thanks a lot, Vincent, for the invitation and the kind introduction. And welcome, everybody. And today I'm going to talk to you about our recent advancement in understanding the energy losses in wide gap perovskite solar system, concentrating, basically focusing on losses happening like at open circuit condition and short circuit condition. And since I see this series of talk more also has a tutorial, I want to brush up on some like basic yet fundamental concept I'm gonna use throughout the talk. So as you all know, like when we have a semiconductor under illumination, we have a photogeneration of free electrons in the conduction band and free holes in the valence band. Now this carrier population cannot be described anymore by one Fermi level, but we need to describe them using like a quasi-Fermi level for electrons and a quasi-Fermi level for holes. The splitting of these two levels is what we call like quasi-Fermi level splitting. And this is an essential quantity that we're gonna use to access the quality of our semiconductor. And I'm gonna just quickly using like two equations, like show you like why this quantity is that important. And the first one is that we can relate the quasi-Fermi level splitting to the free carrier density that we have in our device. So essentially like the magnitude of this quasi-Fermi level splitting correspond to the free density of free electron and holes, which we want to maximize, of course, in a solar cell. The second important relation relate to the fact that we can express the quasi-Fermi level splitting, quasi-Fermi level of electron and holes in terms of chemical potential. And if we have a change in chemical potential of the system, we have also like a change in free energy. So we can think as the quasi-Fermi level splitting has the amount of free energy that we can gain upon an extraction of an electron-hole pair from the system. And then if this change in free energy is in the form of electrical energy, so in electron volts, basically this relates to the VOC of your solar cell. So this to say that like the quasi-Fermi level splitting is a direct measure of the VOC of your device. Now, if you have like an ideal case where the only recombination process that is happening in our device is the recombination of electron and holes through the band gap, through like a radiative process to an emission of the photons, this situation basically represent like a radiative limit. So an ideal scenario, and the magnitude of the quasi-Fermi level splitting in this scenario is what we call like the thermodynamic limit. So it's the maximum splitting of the quasi-Fermi level, and we cannot overcome this limitation. Now, in a more realistic scenario, like our semiconductor will have some defects and trap, which will act as non-radiative recombination centers. And these will act as an additional non-radiative recombination path, which will decrease further the density of electron and holes in our system. And as a consequence, will reduce the splitting of the quasi-Fermi level. Hence, we will have like a lower VOC. Now, on top of that, we have also another type of recombination channel that can happen across the interfaces between the perovskite and the transport layers. For example, here we can have a recombination between an electron and in the ETL and a hole in the perovskite absorber. This is like another recombination channel, what we call like interface recombination. This is also like a non-radiative process, and this will decrease again like further the amount of free carriers that we have in our device, and will decrease further the VOC. Now, we will focus particularly on these processes that can happen like at both interfaces. Now, ideally, we said that the internal quasi-Fermi level splitting should be equal to the VOC that we have in our device. And we see that, that both quantities are influenced by non-radiative recombination processes. So if we want to study the recombination mechanism that is happening in our device, we should be able to access these two quantities. While we can access the VOC quite easily connecting our device like electrically and measure the voltage, the quasi-Fermi level splitting is a bit more tricky. Like we cannot really directly access it like with an easy experimental technique, but there's an easy way around it. And by using the photoluminescence quantum field, we can find a way to access this quantity. If you focus on this relation here, we can express the quasi-Fermi level splitting in terms of photoluminescence quantum yield, the generation carrier, and what we call this J0 rad, which is like the minimum amount of radiative recombination that happens in the dark in our device. I don't want to go like in too much details here, but I just want you to focus on the fact that both the quasi-Fermi level splitting, the photoluminescence quantum yield and this J0 rad are two like easily accessible quantity. So we can directly measure the PIQI of our system, and the J0 rad can be just calculated using an EQE of a solar cell. So the beauty of this technique is that it's a fully optical characterization method. So in order, we can access the quasi-Fermi level splitting, not necessarily having like a full device stack, but we can also just measure like the need absorber just in contact with glass is what we define like as a neat material basically, or in contact with either the HTL or ETL interface in order to disentangle the contribution of recombination of the two interfaces, or in a full device stack. And we will use this approach quite extensively. Now, if we consider that this radiative situation, this ideal case where only charges can only recombine through radiative processes, and we consider another couple of ideal assumption as like perfect like charge extraction or perfect generation above like the bandgap of the material, we can calculate the single junction thermodynamic limit in terms of efficiency that our devices can achieve. Of course, you can see that like this depends on the bandgap, and even when we have like an optical bandgap around between like 1.2 and 1.4, the efficiency of the solar cells of a single solar cell, we cannot like overcome like 35%. However, there is a trick to overcome this limitation, and it's basically just by stacking two solar cells with different bandgaps on top of each other. If you want to do that with like full perovskite, we have usually narrow bandgap perovskite with a bandgap for around like 1.2 eV, and wide gap perovskite with a bandgap of 1.8. When we combine these two, as you can see here, we can have like PCE that like they're above like 40% theoretically, of course, in the ideal case, and this is due to the fact that combining the two devices with different bandgaps, we have like a broader absorption of our solar spectrum. In this talk, we will focus on the wide gap perovskite or the 1.8 eV. So if we look at the 1.8 eV solar cells, perovskite solar cell, we can immediately notice here from this collection of different PIN cells that the VOC, as soon as we move further right from the 1.6 eV device, which is like what we consider like a standard bandgap, we observe like quite a strong limitation in the VOC. So we have a sort of like a saturation of the VOC or a pinning of the VOC to values like of around like 1.2 volts. And the origin of these losses is usually attributed to the fact that we have intrinsic issues in the perovskite material. So either like a large trap density or intrinsic instability of the system, because we have a larger amount of bromide that is usually used to achieve such bandgaps. Arguably, these are the only losses. We'll show that like this, it can be like another type of picture actually here. And just as an example, like to show like where we're at basically of this system, we see that like this is the wide gap perovskite that is being used for, I believe it is still like the current record for whole perovskite tandem. As you can see that like here, for example, they have a around 1.8 eV cells with the VOC around 1.2 volts. So meaning that we still have room for improvement here just on the wide gap perovskite and the whole perovskite tandem as well. I want to focus here on during the talk of like the losses that happens in this system at two operational conditions. The first one is the losses that happen at VOC conditions, so where we have like no extraction of charges, and all the recombination processes that are happening here will directly influence the VOC of your device. And the second operational condition that we're gonna focus on is like a JSC condition. So where in this case, on the contrary, we have like full extraction of charges, or ideally we should have full extraction of charges and no recombination process is happening. And in such a case, like any loss or that we observe at this condition would influence the JSC of our device. Now, before going through like new results, I want to quickly go through what we have learned like recently regarding like the losses at open circuit and short circuit condition in this system. This is a recent publication where we choose like a 1.8 eV model system perovskite, and we modify the perovskite itself using an ionic additive inside, and we improve further the interfaces using lithium fluoride. This we decided to work on this system mostly to investigate the improvement in the VOC and to understand the losses that are related to these such devices. So here we used this PIQY method that I showed before. So we had a look at the PIQY of the knit material, and we compare basically the potential of the PIQY of the knit material to the perovskite when it's in contact either with the HDL or the ETL. And as you can see here, like in PIQY and in also in quasi-Fermi level splitting, when the perovskite is in contact either with the PTAA or the C60, the PIQY and the quasi-Fermi level splitting is like strongly reduced, indicating that in such system we have like strong losses due to interface recombination happening at both interfaces. And here we found out that when we use the ionic additive inside, both interfaces can like optimize basically, and we can like push the quasi-Fermi level splitting higher. These have been also confirmed by time-resolved photoluminescence, which showed like the same trend, and highlighted also how the lithium fluoride can push and optimize the C60 interface even further. But interesting here, like when we looked at these devices, even though like they're quite optimized and they can reach like quite high VOC, when we compare like the quasi-Fermi level splitting and the VOC of the same device, we found out that in all cases, there was quite a large mismatch between the internal quasi-Fermi level splitting and the external VOC. And so we even optimized devices that suffer from this quasi-Fermi level splitting VOC mismatch, meaning that we still cannot achieve the full potential that our perovskite will be able to deliver, basically. And to understand the origin of this a little bit better, we perform like UPS measurements on a sequential deposition of C60 to basically reconstruct the energetic alignment at the ETL interface. And here we found out that in all cases, the ETL present a quite substantial energetic misalignment between the conduction band and of the perovskite and the luma of the C60. And these we know from like previous studies that it can cause a substantial quasi-Fermi level splitting VOC mismatch. To clarify a bit this point, I've shown like at the beginning that the quasi-Fermi level splitting and the VOC should be identical, like in theory. However, we can have a case where we have like strongly misaligned layers, for example, that we have a constant basically injection of carriers from the perovskite to the transport layers. And due to this energetic offset, we cannot have re-injection basically. So we ended up with a strong and large density of majority carriers here in the transport layer, which can recombine with the minority carriers present in the perovskite. And such a scenario would create like a constant depletion of free majority carriers, in this case in the perovskite, causing the banding basically of this quasi-Fermi level splitting. And similarly, we can have like a similar process, like the effect it's the same, but we can have it even though if we have, for example, poor selectivity of the contacts. So this is like a possibility that we can have in our devices. Now, in terms of like JSC losses, here we refer to a recent publication by Jarl. I think she presented these things in this very same series like a couple of months ago. So some of you might be already familiar with the work. And here they investigated especially on lead-tin perovskite, and they essentially like monitor the evolution of the JSC over time in the first like few seconds. And what they found out that due to like an internal ion redistribution in the perovskite, we would ended up with a sort of like internal field screening, where the charge extraction gets limited after a few seconds, and the JSC basically will decay. Now, this study was done on lead-tin perovskite, but they also showed this is quite like a universal process, basically. So universal limitation for different type of perovskite and also for our 1.8 eV. So essentially, we know that like the JSC can be limited due to like this ion screening of the internal field, and limited charge destruction. So now, based on this knowledge of these, essentially like these two important studies, we moved on into understanding a little bit deeper this type of losses in this wide gap system. And first of all, like we have to consider that most of the time, like this wide gap system, or like we say, these perovskite solar cells, the ETL and the HEL are optimized for 1.6 EV devices, which is like the standard ones. When we increase the bandgap of this material, we will end up necessarily with like energetic misalignment between the transport layer and the perovskite. So such a case can influence, of course, the VOC, as we've seen before. So we performed some drift diffusion simulation, looking at the evolution of the VOC depending on the perovskite bandgap. And in two cases, basically, in one case, here the purple one, by constantly aligning the transport layer, so basically simulating like always such a scenario by increasing the bandgap. And we've seen that the VOC increased linearly as we would expect by increasing the bandgap of a perovskite. But when we simulate a case where we keep the transport layer that are optimized for a 1.6 EV cell, we see that the VOCs start to be deviates from this linear increase and start to be like saturated to lower values, increasing more and more the losses the more we increase the bandgap, which is something very similar to what is usually observed experimentally. So we went a little bit deeper here in understanding the losses of this interface by going on with some other simulations. And here, we just wanted to have a look basically at the specific interface or a misaligned when we have like a misaligned transport layer. And if you look at the carrier density profile that we have here, we end up with a very large electron density in the electron transport layer, and which can recombine with a fairly large density of holes here in the perovskite. And these would give rise to quite a large recombination current. Now, such recombination can be described by Shockley Rideau formalism. And we know that if we have a recombination across this interface happening between like unbalanced carrier density, so in this case, large electrons, large density of electrons with like a lower density of holes, the rate of this recombination will depend almost exclusively on the minority carriers, so the holes. So having this in mind, we tried to simulate like an artificial kind of like system where we have the perovskite itself with a surface that is modified in a way where we can decrease the hole density in the proximity of the electron transport layer interface. As you can see here, despite we have still a very large electron density in the ETL, we have a very low or much lower hole density here in the perovskite, and this would give rise to a much lower recombination happening at this interface. And if we look now at the relation between the quasi-Fermi level splitting and the VOC in this system, we can see that like the reference devices, they have like a rather limited VOC with a large quasi-Fermi level splitting VOC mismatch, whereas like in the optimized device, we end up with a much higher VOC, which now matches the internal quasi-Fermi level splitting. So this is like all simulators, but like it started like we use these as like a motivation kind of like to optimize our devices. And now what we did here, we tried like many different type of optimizations. And essentially we focusing on the ETL interface, we modified the perovskite surface using either guanidinium bromide or imidazolium bromide as surface modifiers, or we focus on the HTL interface by inserting like an ionic interlayer between the PTAA and the perovskite. So basically treating the PTAA surface or replacing directly the PTAA with a self-assembled monolayer. Now, these can give rise to a lot of combination of devices, and sorry, this can be like a bit overwhelming, but I just want to guide you through like few like main important points here. The first things that we observe is that treating the PTAA with this ionic layer, the TEA, TFSI, mostly improve like the JSC and the field factor of our devices, of course, like pushing up also the PCE. And whereas like treating like the top interface with guanidinium bromide or imidazolium bromide mostly push up the VOC. reaching like quite nice VOC and resulting efficiencies. So then from here, we try to basically combine the optimization at the bottom interface and the optimization at the top interface. But unfortunately, in this case with PTAA, we didn't really have successful results. So we decide to change basically the PTAA layer with a self-assembled monolayer. And as you can see, like immediately just switching from PTAA to the SAM, we have like a big improvement in the VOC, the JSC, and the fill factor. So basically all parameters like went up. But in this case, what's interesting is that if we can also optimize the top interface with either guanidinium bromide or imidazolium bromide, we can push the VOC much higher, like the surpassing 1.28 volts, which is quite good for this type of devices, and fill factors above like 80% and resulting PCE of like 17%, which is a nice combination of both like HDL and ETL interfaces improvement. So basically, from this combination of improvement, we could find out that the guanidinium and the imidazolium bromide, they effectively improve the VOC of the device. And the TAA-TFSI could mostly like improve the fill factor and the JSC, whereas the SAM could basically push up like all parameters at the same time. And when we combine our best HDL improvement with the best ETL improvement, essentially we can get like these are like record devices where we have like a stabilized like PCE of like 17% and fill factor above like 82 and very high open circuit voltages. And the nice thing of these type of improvements that like if we move from a what we call like small area device to a large area device, we could basically maintain almost all the same parameters. So we have like still fill factor above like 80%, again like PCE around like 17, and in this case like VOCs that of 1.29 volts. So we could really push the efficiencies of this device quite nicely. And in terms of understanding here, like the VOC was quite straightforward, let's say, like it's, or let's say expected to see all these improvement in VOC. What was a bit surprising was to see the improvement in short circuit current upon this interface optimization. So here we don't really have a change in bandgap. We don't really have a change in absorption. So the improvement in short circuit current that we see, they must come from something that is related with the charge structure in our device. So to investigate this further, basically, we adapted the same approach that that has been used in that publication I showed earlier, like for Lentine devices, and we monitored the evolution of the JSC over time. As you can see here, these are like average between like among like multiple devices. The PTAA devices, they always show like a quite substantial like loss in short circuit current over time, whereas when we treat the perovskite with the PTAA with the TAA-TFSI, or when we use the SAM, this loss gets like significantly reduced, which indicates that it's something, again, the improvement in JSC is something related more to the charge destruction. I will go back to these results later to explain a little bit more in details. So now we went on like to characterize a bit all these different device optimizations. And first of all, from just looking at the SEM, we can see that the perovskite, when it's been coated on top of TA, TFSI, or SAM, it already presents like a better morphology. But most importantly, when we look at the top view of SEM of when we treat the perovskite with guanidinium bromide or imidazolium bromide, we see that there's like a clear sort of like recrystallization of the surface. So it really something we are like really modifying something at the perovskite when we spin coat these molecules on top. And then of course, if we look more specifically at what's going on at the surface, we using XRD, we found out that the use of guanidinium bromide and imidazolium bromide always results in appearing of these additional perovskite phases here. This is like an example for the SAM, but it's observed like in all cases. And if we go a little bit deeper here with the XRD analysis, we observe that in all cases where we have like PTA, TA, or SAM, we always observe in the terms when we use like guanidinium bromide or imidazolium bromide disappearing of like low dimensional phases on top of the perovskite, which is being also confirmed by GWAX measurements, which they show like no real preferential orientation of these new phases, but we confirm like having like low dimensional phases on top of the perovskite in all conditions. And now, in order to understand a bit what these optimization did in terms of non-radiative recombination, we used the approach that I introduced before. So we studied basically the photoluminescence quantum yield of the devices, of the material, like the neat material or in contact with the HTL or the ETL. And we can see that already in the neat material, guanidinium bromide and imidazolium bromide, they push the PIQY to higher values, indicating that they act as an effective like surface passivation already in the neat material. But most importantly is when we have the perovskite in contact with the transport layers. In both cases, the best, let's say the best interface optimization, which are like the imidazolium bromide and the self-assembled monolayer, we get to PIQY values, which are really close to the one of the neat material itself, indicating that now interface recombination is not really a major loss anymore. And this was like quite important, but more important is if we look now at the relation between the quasi-Fermi level splitting and the VOC of our devices, we could observe that basically as in the reference device, we have like quite, let's say, limited VOCs and a large quasi-Fermi level splitting VOC mismatch, as you can see here. But when we move to the SAM case, we observe that in the quasi-Fermi level splitting VOC mismatch is completely reduced when we have like a full optimization of the interfaces of the device. And if you remember from the initial simulation, it follows exactly what we predicted that you would have when you have like an optimized device. So we move from like a large quasi-Fermi level splitting mismatch for a reference to like a elimination of a mismatch for like an optimized, fully optimized device. And in terms of photoluminescence, time resolved photoluminescence, the trend follows exactly what we observe from photoluminescence quantum yield as it should be. And so it basically we have, you can see that like in the neat material with the imidazolium bromide, we have the lifetime get pushed up like quite substantially, reaching almost like 7 microseconds, which is quite long. And but again, like more interesting, like when we look at the two interfaces, we can see that like when we use imidazolium bromide, the lifetime gets really close to the one of the neat material. And in the case of the SAM, you can see here that like the two lifetime and are basically exactly the same. So we have almost zero losses induced by these new interfaces. And from the lifetime itself, you can calculate also the surface recombination velocities. As you can see here again, that like the surface recombination velocities that are calculated for the optimized interfaces approach the one of the neat material itself. Again, indicating that in these devices, the interfaces are almost like let's say they don't really induce like a strong recombination channel anymore. And now this was about like the VOC, but what about like the JSC? This JSC improvement. And here we decided to approach this from quite like maybe with an unusual characterization method. And so we decided to record like PL maps of a full device under open circuit and circuit condition. And this is why we did this because like at open circuit condition, you should have like full recombination of charges and like a certain like amount of PL like emitted from your device. But at short circuit condition, ideally, you should have like a full extraction of carriers, and you should have like almost like no PL. We found out that this is not the case, that you always have some residual PL, even at short circuit condition. And basically by comparing the amount of this residual PL that it's still like remaining in the device, we could access like the quality of the charge collection that we have from our device. So we could basically reconstruct these, what we call like charge collection quality maps, where we can basically learn, I would say, like two main things from this map. One is this is like quite large area because it's like, this is like 1 million. So like, it's like 3 millimeter by 3 millimeter. So we can learn something about like large scale inhomogeneities, for example. And you can see that the PTA, we already suffer from some regions where like the extraction of charges is really, really low. So this is something maybe related to like how you process your device. It's more like, yeah, something related to like structure, like defects or whatever when you build the device. But we can also see that like generally, like even when it gets more homogeneous, the extraction of your device, when you have like TA, TFSI, or the SAM, the quality of collection gets like nicely improved. And these again like follow very nicely the like this JSC decay that we observe like in the full devices. So the same trend is basically the two measurements, they qualitatively agree. Now, to understand a bit better what's going on here in charge extraction and why some type of devices extract like more than the others, we decide to perform some other diffusion simulation. In this case, some transient ones. And so we managed basically to replicate the same trend in JSC decay that we experimentally observed. So the PTA, we have like quite a substantial decay. Then the TA, TFSI is less pronounced, and with the SAM is almost reduced. But now having this in a simulation form, we could also have a look at like how the building field evolves like inside the perovskite. And so here we have a look. Basically, this is the thickness of the perovskite. This is the HDL interface. And basically here we're going to have a look at the change in the internal potential of our perovskite, of our solar cell, from the bulk to the HDL. And we can see here that, like, for example, in the PTAA case, we have almost like no change in internal potential across the layer, but like almost all the potential drop across the whole transporting layer. Whereas in the SAM case, in the TA, TFSI case, we have like a change in potential already like in the perovskite. And if we then have a look at the same picture, but in terms of like ion densities, we see that like in the terms of when we have the PTAA, we found out that most of the ions are actually like accumulating in the HDL, so they can diffuse in the HDL and accumulate there. Whereas where we have like a ultra thin SAM, or like when we have this ionic interlayer has a TA, TFSI, we have an accumulation of the ions within the perovskite bulk, or at the interface actually, but not in the HDL. And if we look at the evolution here at the VBI, basically, so the internal field at short circuit condition, we can observe, first of all, that in all cases, we start with a certain field drop, and then due to the ion redistribution, in all cases, we ended up with almost like flat bands in the perovskite bulk, and this was already quite surprising for us. And the only difference that we could notice is that this like remaining field here at the proximities at the HDL interface, that is basically what we observe here. So this is the only difference, and apparently is enough to change drastically the decay of the short circuit current. So we ended up with such a situation, basically, just to schematically represent that in the PTAA case, we have an accumulation of ions in the HDL, where this would cause like a field drop across that layer and flat bands in the perovskite. Whereas like when we have like this ionic layer or the self-assembled monolayer, we have accumulation of ions in the perovskite, and the resulting field that it's maintained in the perovskite, we can help and promote the charge extraction. So lastly, just quickly, I wanted to show you some stability data of these devices. And just to point out that basically here we check like the effect of the guanidinium bromide or the imidazolium bromide in terms of stability. These are like thermal stability at 85 degrees. And as you can see, like compared to the reference SAM devices, the guanidinium bromide made the stability actually worse. So like the devices themselves are like less thermally stable. And the other way around, the imidazolium bromide actually helped the stability. Some of the devices still survive like more than 1,200 hours at 85 degrees. And if we look at the parameters that goes wrong, kind of, it's mostly like the VOC that in the case of the guanidinium bromide is not really maintained. And looking at the film itself stability, we found out that even in air stability, the guanidinium bromide is much less stable compared to the imidazolium bromide that show like basically unchanged absorption profile over 15 days in air. So this just to point out that not all the optimization, like not all the optimization that are good in the device are necessarily like a definitive solution, because you also need to consider if they actually can survive like long time or more like harmful and stress condition. And so here, like to conclude, basically, we found out that in these devices, the JSC is mostly limited by the ion screening and the charge destruction of our device. The VOC, or the other way around, is limited by the energetic misalignment with the transport layer and the quasi-Fermi level splitting VOC mismatch. We found out that optimizing the HDL mostly improved the JSC of our device and helped like the charge destruction, whereas like improving the ETL mostly improved the VOC of the device. And the combination then of the optimized ETL and HDL interfaces give rise like to very high voltages in our device. So, and has a probably like main take-home message here is that these wide gap devices are not necessarily limited by the material itself, and that if you apply like quite appropriate like device engineering and the selection of the transport layers or optimizing the interfaces, you can really access the full potential that the perovskite is able to deliver. And if we now look at the initial plot, when we plot like our devices on top, you can see that like the losses, the VOC losses now that our devices show are like comparable to the normal losses of narrower bandgap perovskite. And just before going to the announcement, I just want to quickly mention that for the past few years, I've been like scientific advisor of this newly founded like startup company in Berlin, and they produce. We help basically optimizing and conceptualizing these PIQIs, small and like compact PIQI setup. So if anyone is interested in having like similar measurements of what I've shown before, and even much more actually in a more like plug and play method than rather than having like a big optical setup, you can get in touch with me or with the guys in Berlin here. And now I want to just to conclude, like thanking like all my group in Oxford, and for the help of all like my colleagues and my former group, and like we're still currently collaborating together, and the funding agency, and of course you for your attention.